59 earthquakes struck the San Andreas fault in 6 days, and every one of them landed on the stretch geologists have spent a century calling harmless. 19 came in a single morning. The largest, a magnitude 3.94, broke 4.5 kilometers beneath a national park in central California at 19 minutes past 3. Nobody was hurt, and no agency said a word, because this piece of the San Andreas cannot store energy. It is the piece that stopped both of California's great earthquakes. So why did somebody drill 3 kilometers into the far end of it and pull up rock carrying the burn marks of more than 100 earthquakes big enough to level a city? One thing before we get into it. If you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs. Drop a comment and tell me where you're watching from tonight. Now let's break this down. Part 1. 3:19 in the morning. At 3:19 and 8 seconds in the morning Pacific time on August 11th, 2026, the San Andreas fault broke. It broke 4.62 kilometers below the surface, about 6 kilometers northwest of a place called Pinnacles in San Benito County, California. The magnitude was 3.94. Nobody was hurt. Nothing fell down. There is no damage report because there is no damage. If you were asleep in Soledad or Hollister, you might have woken up for a second, decided it was a truck and gone back to sleep. And by every ordinary measure, that should be the end of the story. A magnitude 3.94 in Central California is not news. The state produces hundreds of them a year. Nobody issued a warning, nobody raised an alert level, no agency put out a statement, and none of them were wrong not to. But I want to tell you where it happened, because the address is the entire story. That earthquake struck on the central section of the San Andreas fault. And the central section of the San Andreas is the one part of that entire 800-mile monster that the textbooks describe as harmless, not low risk, not manageable, harmless. There is a formal reason for that description, and it is a good one, and we are going to spend a long time on it tonight. But here is the short version, so you know what we're dealing with from the start. Most of the San Andreas is stuck. The Pacific Plate and the North American Plate are trying to slide past each other, and along most of the fault, friction holds them in place. They do not move. They just strain, like a bent branch storing energy, year after year, decade after decade, until the friction gives out and the whole stored load releases at once. That release is an earthquake. That is what happened in 1906 in San Francisco. That is what people mean when they talk about the big one. But along one stretch, roughly in the middle, the fault does not do that. It slides. Continuously, quietly, every single day, at about the rate your fingernails grow. It never sticks, so it never stores, so it has nothing to release. Scientists call it aseismic creep, and the stretch where it happens is called the creeping section. You cannot have a great earthquake on a fault that never stops moving. That is not an opinion, it is arithmetic, and we will do the arithmetic later. So the swarm I want to talk about tonight happened on the one part of the San Andreas that is not supposed to be able to hurt anybody. Let me give you the rest of the numbers on that first shock, because I want you to understand that we are not working from a rumour here. The catalogue entry for the August 11th event is what seismologists call a reviewed solution. That word matters more than it sounds like it should. When an earthquake happens, computers produce an answer within seconds, automatically, from whatever stations have reported in. That automatic answer is often wrong. It gets magnitudes wrong by half a unit. It puts epicenters in the wrong county. It is fast, and speed is the point, and accuracy comes later when a human being sits down with the waveforms and works out what actually happened. The August 11th event has been through that process. 85 separate seismic stations reported it. The azimuthal gap, that is the largest slice of sky, so to speak, with no station in it, and it tells you how well the event is boxed in, was 40 degrees, which is tight. The horizontal error on the location is 140 meters. The error on the depth is 330 meters. Those numbers mean that we know where this earthquake happened to within about the length of a city block, and we know how far down it was to within about the height of a skyscraper. This is not a fuzzy detection. Somebody checked. There is one more detail in that catalogue entry that most people scroll past, and it is worth 30 seconds of your time because it comes up again later. The magnitude 3.94 is a moment magnitude. That is the good one. Moment magnitude is calculated from the actual physical work the earthquake did, the area of fault that moved, multiplied by how far it moved, multiplied by how stiff the rock is. It is a measurement of the event itself. Most of the other earthquakes in this swarm do not have that. They have duration magnitudes, which are estimated from how long the shaking lasted on the seismograph trace, and local magnitudes, which come from how big the wiggle was. Those are perfectly good working numbers for small events, and they are what you use when you have 50 earthquakes a week to process and no time to model each one. But they are estimates of a signal, not measurements of a rupture. So of the 59 earthquakes we're about to walk through, exactly one has been characterized properly. That is not sloppiness. That is triage. But it does mean the largest event in this sequence is the only one we genuinely understand, and it is worth keeping that asymmetry in mind every time I read you another number. And the checking matters, because the thing we're going to be arguing about for the next 2 hours is whether the fault this happened on is the fault we think it is. The 3.94 did not arrive alone. It arrived at the front of a very short line. 1 minute and 33 seconds later, a magnitude 2.57, in almost the same spot 2.6 kilometers down. 20 seconds after that, a magnitude 2.60, this one 4.2 kilometers down. And 57 seconds after that, a magnitude 2.14. 3 more located earthquakes, all above magnitude 2, inside 3 minutes and 33 seconds of the first one. Most of California was still asleep. Then the sequence did something a little unusual, and I want to flag it now because we come back to it. The largest thing to follow, the 3.94, did not follow it immediately. It came an hour and 50 minutes later, a magnitude 2.66, and it was the shallowest significant event of the entire sequence, at 510 meters below the surface. Half a kilometer, that is not far under your feet, that is closer to the surface than most water wells go down. So picture the geography for a second, because it helps. Pinnacles National Park sits in the coast ranges of central California, inland from Monterey, between the Salinas Valley on one side and the Central Valley on the other. It is famous for towers of volcanic rock that rise straight up out of the chaparral and for the condors that nest on them. It is a quiet place. People go there to climb and to walk through talus caves and to look at birds. The San Andreas fault runs along its eastern edge, not near it, along it. Everything in this swarm is happening in the first 5 kilometers of crust beneath that ground. And that shallowness is the first genuinely strange thing on the table, because on this particular stretch of fault, the shallow crust is the part that is supposed to be sliding freely. It is the part with nothing stuck in it. It is the part that, according to the model, cannot store enough strain to break. Something in it broke anyway. Now, what would that have felt like? I want to be honest rather than dramatic here. A magnitude 3.94 at 4.5 kilometers is a sharp, short event. Close in, within 10 or 15 kilometers, it is a bang and a jolt. One hard shove, not a roll. Things rattle on shelves, a hanging light swings. Some people describe it as a truck hitting the house, and some people sleep straight through it. Farther out, in Salinas or Hollister or King City, it is a brief shudder that half the people feel and half the people miss entirely. It does not damage modern buildings. It does not damage old buildings. It is, in every practical sense, nothing. And I want to keep saying that, because the point of tonight is not that this earthquake is dangerous. The point is what it is sitting on top of, because here is what happened in 2022. A team of researchers took rock that had been drilled out of the far end of this exact stretch of fault, from 3 kilometers below the ground, from inside the slipping layer itself, and they ran a chemical technique on it that can detect the heat scar left behind when a fault moves. They found more than 100 of them, and in most of those events the rock says the fault jumped more than 1.5 meters. Hold on to that number. 1.5 meters of slip is not a magnitude 3. It is not a magnitude 4. We will get to exactly what it is, and to the scientists who disagree sharply and publicly about what it means. But I will tell you now that the disagreement is not about whether the marks are there. Everybody agrees the marks are there. The disagreement is about when they were made, and about whether the fault that made them is the same fault that is shaking under Pinnacles tonight. Part 2. 5 days of building. The 3.94 was not the beginning. 4 days earlier, on August 7th, at 27 minutes and 56 seconds past 2 in the afternoon, universal time, a magnitude 3.25 struck at the same spot. 78 minutes after that, a magnitude 3.26. 2 events of essentially identical size, back to back, on a stretch of fault that averages about 1.5 earthquakes a day of any size at all. That was the start. And on that first day, August 7th, the catalogue logged 12 located earthquakes in the immediate area, the 2 3s, plus a 2.89, a 2.66, a 2.24, and a scatter of 1s. August 8th brought 5 more, the largest a 2.77. August 9th brought 5 more, the largest a 2.60, and then August 10th got busy. 17 located events in a single day, and 2 of them are worth stopping on. At 2:39 and 2 seconds in the morning, universal time, a magnitude 2.97. At 2:39 and 55 seconds, 53 seconds later, a magnitude 2.93. 2 earthquakes, 53 seconds apart, at effectively the same magnitude. That combination tells you something specific, and it is worth understanding because it recurs throughout this story. When one patch of fault breaks and then adjusts, you get a big event followed by a smaller one. The second event is the fault settling. But when you get 2 events of the same size back to back, what you're usually looking at is 2 different patches, 2 separate stuck spots side by side, and the failure of the first one loading the second one past its own breaking point almost instantly. That is not a fault settling. That is a fault spreading, and the 2 August 7th events that open the whole sequence have the same signature, a magnitude 3.25 and a magnitude 3.26 78 minutes apart, differing by 1/100th of a magnitude unit. In practical terms, that is the same earthquake happening twice. 2 patches, essentially identical in size, failing in succession. The first one loading the second one waiting an hour and a quarter and then going, which means the sequence did not start with one thing breaking. It started with 2 things breaking, and it ended 4 days later with something breaking that was 30 times more energetic than either of them. Whatever was moving through this reach of fault in that first week of August was not losing strength as it went. Then came August 11th. I want to walk you through the first 38 minutes of that morning the way the instruments recorded it, because reading the sequence in order does something that a summary cannot. 10:19 and 8 seconds, universal time. Magnitude 3.94, 4.62 kilometers down. 10:20 and 41 seconds. Magnitude 2.57, 10:21 and 1 second. Magnitude 2.60, 10:22 and 8 seconds. Magnitude 2.14, 10:32 and 3 seconds. Magnitude 1.77, 10:34 and 58 seconds. Magnitude 1.58, 10:46 and 59 seconds. Magnitude 0.99, 10:57 and 38 seconds. Magnitude 1.9, 8 located earthquakes in 38 minutes, and then the sequence kept producing them all day, roughly 1 hour into the evening. 23 located earthquakes in that universal time day. That hour-by-hour drumbeat is worth noticing, because it is not what a decaying aftershock sequence sounds like. Aftershocks obey a decay law. It is called a Maury's law. It has been known since the 1890s, and it says the rate of aftershocks falls off roughly in proportion to 1 over the time since the main shock, which means the first hour after a main shock should be dramatically busier than the 6th hour, and the 6th hour should be busier than the 12th. 8 events in the first 38 minutes fits that. 1 an hour, steadily, 12 hours later, does not fit it nearly as well. Something kept feeding this sequence after the largest event had already happened. Counted by Pacific Calendar Day, which is how the people living there would experience it, August 11th holds 27 located events. 27 earthquakes under one national park in one day. And on August 12th, as this was being put together, the sequence was still going. 7 events by early afternoon in universal time, the largest a 2.08. Slower, not stopped. Now, I have given you a lot of numbers, and I want to pull the shape out of them because the shape is the interesting part. A normal earthquake sequence has a very particular signature. The biggest event comes first. That is the main shock. Everything after it is an aftershock, and the aftershocks get smaller and less frequent over time, following a decay curve so reliable that it has a name and an equation attached to it. Big event, then a tail. That is what almost every earthquake sequence on Earth looks like. This one did the opposite. It opened with 2 magnitude 3s, ran for 4 days without dying, and then peaked on day 5. The largest event in the sequence arrived after the sequence had already been running for 92 hours. That ordering has a name too. It is called a swarm, and a swarm means something mechanically different from a main shock. A main shock is one patch of fault reaching its limit and letting go. A swarm is something moving through the fault and loading a series of patches in turn, something that arrives, does its work over days, and leaves. So the sequence is telling us it is a swarm, except for one measurement, which says the opposite. There is a rule of thumb in seismology called Barth's law, and it says that the difference in magnitude between a main shock and its largest aftershock tends to be around 1.2, more or less regardless of the size of the main shock. It is an empirical rule rather than a law of physics, but it holds up remarkably well across enormous numbers of sequences. The magnitude 3.94 was followed at its largest by the magnitude 2.66. The gap between them is 1.28. That is almost exactly what Barth's law predicts for a main shock and its aftershock. So we have a sequence whose build-up says swarm and whose aftershock structure says main shock. It is doing both things at once, and that is not a contradiction so much as an admission that our categories are cruder than the fault is. And that, more than anything else, is why no agency has said anything about this. Not because it is being hidden, because nobody can currently tell you which of those two things it is, and the honest professional answer to a question you cannot answer is silence. There is a second reason for the silence, and it is more interesting than the first. A swarm and a main shock demand completely different responses. If the 3.94 was a main shock, the sequence is over, the fault has released what it had, and the aftershocks will thin out over the following week. If it was a swarm, then whatever was driving it, and we will get to the candidates that may not be finished, and the largest event may not have happened yet. Those two readings point in opposite directions, and there is no instrument you can point at the ground that will tell you which one you are in while you are in it. You only find out afterwards. That is not a failure of the science. It is the actual nature of the problem. The total, across the 6 days from August 7th through the 12th, inside a box about 30 kilometers on a side centered on pinnacles, is 59 located earthquakes. Widen the box to take in the whole reach of fault from Interlaken in the north to San Andreas in the south, and the count for the same window rises to 71, 59, which on its own means absolutely nothing to you. It is a number without a scale. It could be 100 times normal or it could be a slow week. The only way to know is to ask what that specific patch of ground does when nothing is happening at all. And it turns out we can answer that question with real precision. Part 3, 6.8 times normal. Between January 1st and August 7th of this year, 218 days, the same box of ground recorded 313 located earthquakes. 313 divided by 218 is 1.44 earthquakes per day. That is what the ground under pinnacles does when it is behaving. The swarm produced 59 earthquakes in 6 days. 59 divided by 6 is 9.83 per day. 9.83 divided by 1.44 is 6.8. The swarm ran at nearly 7 times the normal rate for that patch of the San Andreas fault, and it held that rate for 6 consecutive days. I want to be careful about what that number is and is not. It is not a spike. A spike is what you get when one moderate earthquake sets off 2 hours of aftershocks and the daily count blows out and then collapses. This is not that. This is a sustained multiplication of the background rate, measured against the same box with the same instruments in the same year over almost a week. That is a real change in behavior, not a statistical wobble. And now the counterweight, because this channel does not do one without the other. Since 1990, 36.5 years, that same box has produced 61 earthquakes of magnitude 3.5 or larger. That works out to about 1.7 per year. So an earthquake the size of the August 11th event happens on this patch roughly every 7 months. It is uncommon. It is not rare. It is certainly not unprecedented. If you'd been watching this fault for the last 3 decades, you would have seen something like this about 60 times. And there is a further check worth running on the swarm, which is the shape of its magnitudes rather than the count of them. Earthquakes obey a very reliable relationship called the Gutenberg-Richter law. For every earthquake of a given size, you get roughly 10 times as many 1 magnitude units smaller. 10 magnitude 2s for every magnitude 3, 100 magnitude 1s for every magnitude 3. That ratio holds across almost every fault system on the planet, and when it breaks, it is genuinely informative. An unusual excess of larger events relative to smaller ones can indicate a fault under high stress. Look at the 59, 1 event above 3.9, 2 above 3, a handful in the 2s, a long tail of 1s and below. That is, as far as a rough count can tell you, an ordinary distribution. The swarm is producing more earthquakes than usual, but it is producing them in the usual proportions, which is one more reason nobody has raised an alarm, and one more reason the count on its own is not the story. Then there is the question of how much energy was actually involved, and here the numbers collapse in a way that is genuinely useful to understand. Every whole step up the magnitude scale is about a 32-fold increase in the energy an earthquake radiates, not 32%, 32 times. Run that out. The magnitude 3.94 released roughly 900 times less energy than a magnitude 5.9. Against a 1906 scale rupture, a 7.9, it is smaller by a factor of around 1 million, and if you add up every single one of those 59 earthquakes, hook them all together, the total is still a small fraction of 1 magnitude 5. So the swarm is nearly 7 times the normal rate, and it is energetically trivial. Both of those are true, and the resolution between them is the thing I want you to take out of this section. The anomaly is in the pattern, not in the power. Nothing about the energy release here is remarkable. What is remarkable is that 35 kilometers of the San Andreas fault changed its behavior for 6 days, and then, in the middle of doing so, produced the largest event this specific patch has generated in almost 15 years. Let me show you the 35 kilometers, because the geometry matters. Start with the depths across the whole sequence. They run from about 300 meters below the surface down to 5.5 kilometers, with most of the events clustered between 2 and 5. One event, at 29 minutes and 57 seconds past 11 in the morning Universal Time on August 11th, was logged at a nominal depth of minus 0.24 kilometers, which in a catalogue means the calculated hypocenter came out slightly above sea level datum. In terrain like this, that is a way of saying it happened essentially at the ground surface. None of this is happening far down. All of it is happening in the top few kilometers of crust, and it is not happening in one place. It resolves into 3 distinct clusters. The main cluster sits 4 to 8 kilometers northwest of Pinnacles, between 36.55 and 36.59 degrees north. This is where the 3.94 struck, and where most of the 59 events sit spread through that shallow zone from 300 meters to 5.5 kilometers. The second cluster sits 7 to 11 kilometers southeast of Pinnacles, down around 36.45 to 36.48 degrees north. Its events are smaller, magnitudes 1.87 to 2.49, and they sit farther down between 4 and 8 kilometers. It was active on the 8th, the 10th, and the 11th. The third cluster sits at the other end, up near the towns of Tres Pinos and Ridgemark, between 36.68 and 36.78 degrees north. Magnitudes 1.13 to 2.60, depths from 6.3 to nearly 12 kilometers. It was active on the 9th and the 10th. Lay those 3 clusters end to end, and you have activity spread across roughly 35 kilometers of fault trace on overlapping but not identical days at 3 different depth ranges, and the northwest cluster is systematically farther down than the main one. Now, I have to add a caveat here, and I would rather add it than have you find it later. That depth gradient might be real structure. It might also be an artifact. Earthquake depths are the hardest parameter to measure well, and how accurately you get them depends heavily on how many stations you have and where they sit relative to the event. A cluster sitting off to the side of the network's best coverage will systematically get pushed to different depths than one sitting right underneath it. From catalogue data alone sitting here, I cannot tell you which of those it is. What I can tell you is that 35 kilometers of the San Andreas fault did something unusual over 6 days in August, and that the official position, the one in the textbooks, the one in the hazard models, the one every geology undergraduate in California learns in their second year, is that this particular 35 kilometers is structurally incapable of producing a dangerous earthquake. That position has a name, it has a mechanism behind it, and it has 2 enormous pieces of historical evidence supporting it, both of which involve earthquakes that killed people. It is worth understanding properly before anybody tries to knock it down. Part 4. The Fault That Refuses to Stick. The San Andreas is not one fault behaving one way. It is 3 sections that behave so differently from one another that they might as well be 3 separate faults that happen to be touching. Get that idea in your head, and the rest of tonight makes sense. Miss it, and none of it will. Start at the top. The northern section runs from Cape Mendocino down past San Francisco to about San Juan Bautista, and it is locked. Friction holds the 2 plates against each other, and they do not move relative to one another, not by millimeters, not by anything you could measure with a tape. They just load. And on April 18th, 1906, the northern section stopped holding. 477 kilometers of fault ruptured in about a minute, magnitude 7.9, and around 3,000 people died, most of them in the fires that followed, which is its own grim lesson about what actually kills people in earthquakes. Now go to the bottom. The southern section runs from about Parkfield down through the Carrizo Plain, past Cajon Pass, and out toward the Salton Sea, also locked. That section, and the tangle of faults associated with it, produced the 1994 Northridge earthquake, magnitude 6.7, around 60 dead, $20 billion in damage from an event that was, by San Andreas standards, small. A great many seismologists believe the southern San Andreas is currently loading towards something on the scale of 1906. And then there is the piece in the middle. The central section runs about 150 kilometers from San Juan Bautista in the northwest down to a village called Parkfield in the southeast. And it does not lock, it slides. Here is what that means physically, because the words creep and lock are doing an enormous amount of work, and it is worth unpacking them properly. 2 blocks of rock are pressed together and pushed in opposite directions. What happens next depends on friction. If the friction between them is high, if the surfaces are rough or clean or clamped hard enough by the weight of the rock above, then the blocks stick. The pushing continues regardless. It does not care that the fault is stuck. So the rock on either side starts to deform, bending elastically, storing the energy of that motion in itself the way a drawn bow stores the energy of your arm. That storage can go on for a very long time, decades, centuries, and then the friction gives way at one point, and the stored energy in a colossal volume of rock releases at once, and the 2 sides snap past each other in seconds. That is an earthquake. Everything about it, the size, the duration, the shaking, is a function of how much was stored and how much of the fault lets go. Now change one variable, make the friction low, make the fault surface slippery, whether because of the minerals in it or the fluids in it or the way it has been ground down over millions of years. Now the blocks never stick in the first place. They just slide continuously at whatever rate the plates are pushing them. And if they never stick, they never store. And if they never store, there is nothing to release. That is a seismic creep. It is not a theory. You can watch it happen. In Hollister, at the northern end of this section, the fault runs directly through a residential neighborhood, and you can walk down the street and see it. Curb stepped sideways, a sidewalk sheared into an S-curve, garden walls slowly torn in half, one house with a driveway that no longer meets the road it used to meet. Nobody in Hollister has ever felt those things happen. They just look at them one year and notice they are worse than last year. A few miles south of town on Cienega Road, there is a winery whose main building the fault runs directly underneath. The floor is cracked in a line, and the 2 halves of the building are slowly going in opposite directions. They have been repairing it for decades. They will be repairing it forever. It is one of the few places on Earth where you can buy a glass of wine while standing on a plate boundary and watch the plate boundary work. So why is this stretch slippery when the rest of the fault is not? That question has occupied a lot of careers, and the leading answers involve the minerals that happen to be sitting inside the fault zone here. This part of Central California is threaded with serpentinite, a slick, greenish, altered rock derived from oceanic mantle that got scraped into the continental margin, and serpentinite is weak. Weaker still are some of its relatives. When cuttings came up from the borehole at the southern end of this section, one of the things found in the fault gouge was talc, which is quite literally the softest mineral on the standard hardness scale. It is what talcum powder is made of. A fault zone lubricated with talc and serpentinite does not behave like a fault zone made of granite. It does not lock, because the material inside it cannot hold. That is the physical explanation for the arithmetic we are about to do. The numbers behind this are what turn the story into arithmetic. Surveys of the creeping section put the surface creep rate between 26 and 33 millimeters a year, depending on where along the section you measure and what technique you use. Call it 30 for a working figure. 30 millimeters a year is a little over an inch. It is roughly the rate your fingernails grow. And the long-term slip rate of the San Andreas fault as a whole, the amount the plates actually demand, worked out independently from geology and from satellite geodesy, is 34 millimeters a year, plus or minus 3. Sit with those 2 figures for a second. The plates are asking for 34. The creeping section is delivering somewhere between 26 and 33. The gap between what is demanded and what is delivered is called the slip deficit, and the slip deficit is the strain that gets stored. It is, quite literally, the earthquake in waiting. Here, that gap is close to zero. That is the whole safety argument for the central San Andreas, and it fits in one subtraction. The fault is paying its bill. There is nothing left over to accumulate, which is why, over a human lifetime, say 80 years, this fault quietly moves about 2.5 meters, 8 feet, 2 adults lying head to toe. That much ground has slid past itself since the 1940s, right underneath Hollister, without producing a single damaging earthquake. And then there is the historical evidence, which is the part that turned a mechanism into a doctrine. On January 9th, 1857, the southern San Andreas ruptured in the Fort Tillon earthquake. Magnitude around 7.9, 360 kilometers of surface break, one of the largest earthquakes in the recorded history of North America. It tore northward up the fault, through the Carrizo Plain, toward Parkfield, and then it stopped. It did not carry on into the central section. It ran up to the edge of the creeping ground and it died there. 49 years later, the 1906 rupture came the other way. It tore southward from the epicenter offshore of San Francisco, down the peninsula, past Los Gatos, towards San Juan Bautista, and then it stopped, at the northern edge of the same structure. Two of the largest earthquakes in Californian history, generations apart, running in opposite directions, both terminating at the two ends of 150 kilometers of creeping fault. That is not a model. That is not a simulation. That is the fault's own record of what it did, twice, and it is the reason the creeping section has been treated for the better part of a century as a permanent wall, a stretch of ground that cannot store energy, and more importantly will not let anybody else's energy through, which is a genuinely reassuring picture. And to hold it, you have to believe that a fault sliding at 30 millimeters a year, for millions of years, has left no evidence of ever having done anything else, so somebody went and checked. Part 5. A volcano cut in half. The rock towers that give Pinnacles National Park its name are the reason people go there. They rise straight out of the brush, hundreds of feet of red and gold breccia riddled with caves and chimneys, and condors nest on the high ledges. They are volcanic, and they are half of a volcano. The other half is 400 kilometers away near Lancaster, in the Antelope Valley on the northern edge of Los Angeles County, where it is called the Neenach Volcanic Formation. It is not much to look at. Low hills, scrub, a landform most drivers on the highway would never register. But the two of them were once the same volcanic field. One eruption sequence, one set of rocks, one place. They are now separated by roughly 195 miles, 314 kilometers, and the thing that separated them is the fault running along the eastern boundary of Pinnacles National Park. The same fault that produced the swarm we have been talking about all night. The correlation was published by Matthews in the Bulletin of the American Association of Petroleum Geologists in 1976, and it became one of the founding demonstrations that the San Andreas is not a crack but a conveyor. Here is how you make an argument like that, because it is not as simple as noticing two piles of volcanic rock and deciding they match. Volcanic formations have fingerprints, not one feature, but a whole stack of them. The specific chemistry of the lava, the sequence of eruptions from bottom to top, the thickness of each flow, the mineral assemblages, the way the units are layered on top of one another and what sits underneath them. Two unrelated volcanoes can share any one of those. Sharing all of them, in the same order, is effectively impossible, and it is worth saying what those rocks actually are because volcanic covers a lot of ground. The Pinnacles Formation is not a neat cone of layered lava. It is the shattered remains of a violent, explosive volcanic centre, thick sheets of rhyolitic and andesitic breccia, which is to say rock made of angular fragments of older rock welded together in a matrix, laid down by eruptions that blew the volcano apart rather than building it up. That is why the park looks the way it does. Breccia weathers unevenly. The tough parts stand up as towers, and the weak parts wash out between them, which is how you end up with a landform full of spires, slots and caves formed by boulders that fell into narrow gorges and jammed there. Pinnacles and Neenach share all of them. Same rock types, same sequence, same age, around 23 million years, and crucially the two formations sit on opposite sides of the fault, one on the Pacific Plate and one on the North American Plate, exactly where you would put them if you took a single volcanic field, cut it down the middle, and dragged one half northwest for 23 million years. which is what happened. I find this one of the more affecting facts in California geology, and I want to say why without overselling it. People drive to pinnacles, hike up through the Talus caves, get to the top of the high peaks, and look out. And what they are standing on is a volcano that has been carried 200 miles away from the other half of itself. It did not erupt there, it arrived there. The ground they parked on is a passenger, and the 59 earthquakes we have been counting all night are that same journey, continuing on a Tuesday in August. Now, if you are the sort of person who checks arithmetic, and I hope you are, you may already be reaching for a calculator, so let me get there first. 34 millimeters a year, over 23 million years, is about 780 kilometers. But the offset between Pinnacles and Neenach is 314. Those do not match, and they are not supposed to. 2 reasons. The first is that the San Andreas fault as we know it today is younger than 23 million years. The plate boundary has reorganized itself repeatedly, and the specific trace that carries the motion now has not been carrying it for the whole time. The second is that the Pacific North American boundary is not one fault. It is a system perhaps 100 kilometers wide, and the motion is shared between the San Andreas, the Hayward, the Calaveras, the San Jacinto, the Eastern California Shear Zone, and a dozen other structures. The San Andreas takes the largest share. It does not take all of it. So the arithmetic is not a paradox. It is a reminder that this fault is one lane on a very wide highway. There is a second thing the Pinnacles-Neenach pair tells you, and it is the one that matters most for tonight. It tells you the direction. The Pacific side, the side Pinnacles sits on, has moved northwest relative to the North American side. Everything west of the fault at that point, including the volcano, including the towers, including the parking lot, is riding north. Given enough time, Pinnacles will pass Hollister, then San Juan Bautista, then the latitude of San Francisco. That is not speculation about a possible future. It is a continuation of a motion that is already 23 million years old and has not stopped once. The only question has ever been whether it happens quietly or all at once. But the point that the 314 kilometers does make, unambiguously, is this. On the timescale that matters to rock, the central San Andreas does not pause. Its default state is motion. It has been in motion for a period of time that makes the entire history of human civilization a rounding error. And it was in motion this morning, and it is in motion right now. Which raises an obvious problem with everything I said in the last section. If this stretch of fault genuinely slides freely, if nothing on it is stuck, then nothing on it should be capable of breaking. There should be no magnitude 3.94. There should be no swarm. There should be nothing at all except silent, continuous, undramatic movement. So why has one specific spot underneath Pinnacles broken, over and over, at almost the same size, on almost the same schedule, for at least the last 77 years? Part 6. The patch that keeps its schedule. October 22nd, 1949. Magnitude 4.7. July 29th, 1951. Magnitude 5.0. January 14th, 1986. Magnitude 4.8, 6.2 kilometers down. July 26th, 1988. Magnitude 4.7, 3.18 kilometers down. April 23rd, 1995. Magnitude 4.9, 6.6 kilometers down. August 27th, 2011. Magnitude 4.64, 7.5 kilometers down. Every one of those earthquakes happened inside a patch of ground you could walk across in an afternoon, in the shallow crust northwest of Pinnacles, on the fault that is supposed to slide freely. And the last one on that list, the 2011 event, sits approximately 600 meters from the hypercenter of the earthquake that woke people up on August 11th. 600 meters, 14 years, 11 months, and 15 days apart. So the safety argument has a hole in it, and the hole has a name. It is called an asperity. An asperity is a stuck patch inside a fault that is otherwise sliding. Picture the fault surface not as a smooth plane, but as a rough one, mostly slick, with occasional hard spots where the rock is stronger, or the surfaces interlock, or the fluid pressure is lower and the clamping force is higher. The slick parts creep, the hard spots do not, and that produces a very specific mechanical situation. The stuck patch is surrounded on all sides by fault that is moving. Every year the ground around the asperity slides 30 millimeters, and the asperity itself slides 0. So the patch gets dragged at its edges, loaded not by the plates directly but by its own neighbourhood, at a rate set by the creep of the fault around it. Then it fails. It catches up all at once. That is your earthquake. And because the loading rate is essentially constant, because creep does not speed up and slow down much over decades, the interval between failures is roughly constant too. The patch keeps time, not perfectly, not to the year, but it keeps time. Look back at that list with that idea in hand. 1949, 1951, 1986, 1988, 1995, 2011, 2026. Magnitudes between 4.6 and 5.0 for the first 6, and now a 3.94. A patch loaded by its neighbours, failing at a similar size, at intervals of a decade or two. Under this reading, the August 11th earthquake is not a warning about anything. It is a stuck spot doing exactly what it has been doing since before anybody watching this was born. That is one explanation, and it is a good one. But it is not the only one on the table, and the second one accounts for something the asperity model does not. The asperity model explains one earthquake. It does not obviously explain 35 kilometres of fault becoming active over 6 days. So here is the second candidate, a creep transient. The creeping section does not creep at a perfectly steady rate. It comes in episodes. For weeks or months the fault moves at its background rate, and then for a period of days a stretch of it will slide faster, sometimes several times faster, and then settle back down. These are called creep events, and they have been recorded on this fault with instruments called creep meters, which straddle the fault trace and measure the two sides pulling apart for more than 3 decades. Now imagine one of those episodes propagating through the ground beneath pinnacles. As the accelerated slip passes each stuck patch, it loads it faster than usual. Patches that would not have failed for another 5 years fail this week instead. And because the transient moves along the fault, the earthquakes it triggers move with it. That would explain the 4-day build-up. It would explain 35 kilometres of involvement. It would explain why the largest event came late rather than first. And it would explain why the depths are so shallow, because creep transients live in the shallow part of the fault. One mechanism, 4 observations. That is the kind of economy that tends to indicate you are looking at the right answer. And there is a third possibility layered underneath both of them, which is fluid. Episodic creep on this fault has been attributed in the published literature to variations in pore pressure, the pressure of water held in the pore spaces of the rock inside the fault zone. Raise that pressure, and you push the two sides of the fault apart very slightly, which reduces the force clamping them together, which makes slip easier at lower stress. It is the same physics as a hovercraft, applied to a continental plate boundary, and swarms specifically, as opposed to main shock-aftershock sequences, are strongly associated with fluid-driven processes in essentially every tectonic setting where they occur. Volcanic swarms, geothermal swarms, induced swarms next to wastewater injection wells. Fluid moves, pressure changes, and the fault produces a long string of similar-sized events instead of one big one and a tail. I want to be very clear that nothing in the available data demonstrates a fluid pulse under pinnacles. What I am telling you is that the sequence has the shape that fluid-driven sequences tend to have. Now all 3 of those hypotheses are testable, and they are testable with data that exists. The creep meter and alignment array network across this section has been running for over 30 years. If a creep event passed through the pinnacle's reach between the 7th and the 12th of August, those instruments recorded it. If nothing moved, the asperity reading gets stronger by default. That data was not available when this was put together. It is the single most useful thing anybody could pull for this story, and I would love to see it. And I want to be honest about which way I lean, because I think you deserve that rather than a shrug. The 3 clusters bother me. A single asperity failing explains one earthquake beautifully, and explains 35 kilometres of simultaneous activity not at all. Something link those 3 patches over 6 days, and the only candidate on the table that links things over distance and time without releasing measurable energy is a seismic slip. But leaning is not knowing, and I have been wrong about sequences before. Back in May, in our video on the Parkfield clock, we spent an hour on the idea that a stretch of fault can keep time, that the same patch can break at the same size at regular intervals, well enough that people tried to schedule the next one. There, the events were magnitude 6s. Here, the same idea is being applied to magnitude 5s and a magnitude 3.94. Same physics, smaller patch, shorter clock, and for scale, Before we move on, this segment can do considerably better than a 5. On April 9th, 1961, at 23 minutes and 21 seconds past 7 in the morning Universal Time, a magnitude 5.88 struck 10 kilometers southeast of Tres Pinos, 12 kilometers below the surface. It remains the largest instrumentally recorded earthquake anywhere in this segment. And 2 minutes and 20 seconds later, at 25 minutes and 41 seconds past 7, a separate magnitude 5.5 struck 12 kilometers south of Tres Pinos. A doublet. 2 substantial earthquakes 2 minutes apart on a fault that cannot store energy. One more date, and I am flagging this one as a coincidence because that is exactly what it is. On August 12th, 1998, 28 years to the day before the swarm data in this video was compiled, a magnitude 5.1 struck 10 kilometers southwest of Ridgemark at the northwestern end of this same system, 8.8 kilometers down. Nothing connects the two. The calendar is not a mechanism, but it is a useful reminder that this ground has a long habit of producing events in this range, and that a magnitude 3.94 is not the ceiling here. So every explanation on the table says the same thing. The creeping section can produce 4s, it can produce 5s, it cannot produce anything worse, because there is nothing stored for anything worse to release. And in 2022, a team of researchers pulled rock out of this fault that does not fit any of those explanations at all. Part 7. 3 kilometers into the fault. Everything we have covered so far is inference from the surface. We have counted earthquakes recorded by instruments sitting on top of the ground. We have measured creep by watching fences bend. We have matched 2 piles of volcanic rock across 400 kilometers of California. All of it is good science, and all of it is indirect. Nobody in that entire chain of reasoning has ever touched the fault. There is exactly one place on Earth where somebody went and got it. To explain how that happened, I have to take you to the other end of the creeping section, to a village called Parkfield. It sits in the hills of Monterey County, about 130 kilometers southeast of Pinnacles, and its permanent population is in the low dozens. There is a bridge there that crosses the San Andreas fault, with a sign at each end telling you which tectonic plate you're entering. The town's own sign calls it the earthquake capital of the world. That is not a joke, and it is not tourism. Parkfield earned it. Because Parkfield sits exactly where the creeping section ends and the locked fault begins, and something about that transition produces earthquakes on a schedule. Here is the list: 1857, 1881, 1901, 1922, 1934, 1966. Every one of them a magnitude 6, give or take, in essentially the same place. Average the intervals and you get about 22 years, and essentially the same place undersells it. When you overlay the seismograms from successive Parkfield earthquakes, the waveforms are almost interchangeable. The same pattern of arrivals, the same shape, the same duration. 2 earthquakes only produce matching waveforms if they happen on the same patch of fault, with the same geometry, releasing the same amount of energy in the same direction. It is a fingerprint. What those recordings are telling you is not that Parkfield produces magnitude 6s. It is that Parkfield produces the same magnitude 6 over and over, like a stuck key on a piano. Now, if you are a seismologist and somebody shows you a fault that has produced 6 similar earthquakes at roughly 22-year intervals, you do something about it. And in 1985, the United States Geological Survey did. It issued a formal prediction that the next Parkfield earthquake would occur before 1993, and it built the most heavily instrumented patch of ground in the world around the fault to catch it. Creep meters, strain meters, magnetometers, laser ranging, borehole seismometers, water well monitoring, a trap essentially set for an earthquake. 1993 came. Nothing happened. 1995. Nothing. 2000. Nothing. The Parkfield earthquake finally arrived on September 28, 2004. Magnitude 6.0. 38 years after 1966, in a sequence whose average interval was 22. It overshot by 16 years, most of a human generation past the forecast window. That failure did more for earthquake science than a success would have. It is the reason the phrase characteristic earthquake is now said with a raised eyebrow rather than a straight face. It is the reason no responsible seismologist in this story will give you a date. And it is worth remembering tonight, because everything I am about to tell you about 100 ancient ruptures comes with that lesson attached. Faults have habits, and habits are not schedules. but the trap was still set, and when the 2004 event finally came, it was recorded in more detail than any earthquake in history. It also broke the pattern in a second way that nobody had planned for. The 1966 earthquake nucleated at the northwestern end of the Parkfield patch and tore southeast. The 2004 earthquake nucleated at the southeastern end and tore northwest. Same patch, same size, opposite direction. That matters more than it sounds like it should, because the direction a rupture travels controls where the worst shaking lands. Energy piles up in front of a rupture the way sound piles up in front of a supersonic aircraft, so the towns at the far end of the tear get hit substantially harder than the towns behind the starting point. Two earthquakes that look identical on paper can deliver completely different amounts of damage depending on which way they went. The characteristic earthquake was not just late, it was also, in the way that would actually matter to anyone living there, a different earthquake. Which brings me to the hole in the ground. The San Andreas Fault Observatory at depth, everyone calls it SAFOD, is a borehole 3.2 kilometers long, drilled starting in 2004 from a pad on the western side of the fault at Parkfield. It does not go straight down. It goes down and then bends, angling across so that the bottom of the hole passes directly through the active trace of the San Andreas at a depth of around 3 kilometers. Think about what that requires. You're aiming a drill string at a plane of rock you cannot see, kilometers underground, that is itself moving. And the target is not enormous. The actively slipping part of a fault zone can be a couple of meters wide. They hit it. Twice, on two separate active strands, which they identified because the steel casing of the borehole began to deform as the fault sheared it. The instrument that proved the drill had hit the fault was the drill hole itself, being slowly bent. I want to sit on that image, because it is one of the more remarkable things in modern geology. Engineers cased a hole with steel, 3 kilometers underground, and then went back and measured it again later, and found that in two narrow intervals a couple of meters across the steel was no longer round. The plate boundary was quietly crushing their casing out of shape, in real time, while they watched. Not in an earthquake, just on an ordinary day, at the rate a fingernail grows. The project ran in stages, a pilot hole first, to characterize the rock, then the main hole, drilled down and angled across the fault. Then, in a later phase, they went back and drilled short side branches off the main bore specifically to recover core from the actively deforming zones. Because the first pass had located the fault, and now they knew precisely where to reach. That last phase is the one that matters tonight, because that is where the rock came from. It is also worth knowing what a project like this costs, in the sense of what it competes with. Scientific drilling on this scale is expensive, slow, and prone to disaster. Holes collapse, drill strings get stuck, target zones turn out to be somewhere other than where the seismic imaging said they were. A hole 3 kilometers long, angled to intersect a moving plane of crushed rock, is a serious engineering gamble funded on the argument that you cannot understand a fault by only ever looking at it from the outside. The point of all this was to stop inferring and start measuring. Stress, fluid pressure, temperature, friction, mineralogy, the physical properties of a plate boundary at the depth where earthquakes actually nucleate, measured in place, rather than reconstructed from a seismogram 30 kilometers away. And they brought rock back up, cores, cylinders of the fault zone itself, including the sedimentary rock caught inside the slipping layer. Now here is the detail that makes this borehole the hinge of the entire video, and it is a detail of geography rather than of science. SAFOD was drilled at Parkfield. Parkfield is the southeastern end of the creeping section, which means the rock they pulled out of that hole is creeping section rock. It is a physical sample of the exact structure that stopped the 1857 rupture, the exact structure that stopped the 1906 rupture, and the exact structure that has been producing earthquakes under pinnacles for the last 6 days. Before we go into what was in it, one more thing about this end of the segment, because it is where the stakes live. Parkfield is a transition. It is not a line where creep stops and lock starts. It is a reach of fault where the proportion of stuck ground increases as you move southeast, until eventually the fault is entirely stuck. And southeast of that transition is the Carrizo Plain, the reach that ruptured in 1857 and has not ruptured since. 169 years ago. Every year the creeping section slides about 30 millimeters, and every year that slip has to be accommodated by whatever sits at the end of it. The creeping fault does not just relieve stress, it also delivers it continuously to the locked ground next door. Think of a zip fastener that is half undone, The open half has no tension in it at all, but the point where the open half meets the closed half, that single tooth, is carrying everything. Move the slider a little further, and you have not reduced the load on the fastener. You have concentrated it on the next tooth down. That is what a creeping segment does to a locked one. The creep is not a release valve for the whole system. It is a release valve for itself, which loads the boundary. And the boundary here is a village of a few dozen people with a bridge over the fault, southeast of which lies 169 years of stored motion. That is the geometry. The shaking is at one end of this segment. The rock that tells us what the segment can do came out of the other end, and what was in that rock was not a fossil, and it was not a mineral, and it was not anything anyone was expecting to build a hazard argument on. It was burnt organic chemistry. Part 8. Burnt molecules. When a fault slips, the two surfaces grind against each other at speeds of about a metre per second, for a few seconds, under the weight of several kilometres of rock. That does what friction always does. It makes heat. And in a slip zone only millimetres wide, with nowhere for the heat to go in the time available, the temperature does not rise politely. It spikes, hundreds of degrees above the surrounding rock in seconds, and then it bleeds away over the following hours and days as the rock around it soaks it up. For most of the history of geology, that heat pulse was a lost signal. It happens, it dissipates, and the rock cools back down to the temperature of its neighbours. There is nothing left to find, except in sedimentary rock there is. Because sedimentary rock contains the chemical remains of living things, organic molecules called biomarkers, laid down with the sediment and preserved for millions of years. These are not fossils in the sense of bones or shells. They are molecules. When bacteria and algae died and settled into the mud of an ancient seafloor, the tough lipid components of their cell membranes did not rot away with the rest. They survived, buried, as distinctive carbon skeletons with names like hopanes and steranes, structures so specific that a petroleum geochemist can look at the mixture in a rock and tell you roughly what kind of organism made it and what kind of water it lived in. And organic molecules are fragile in a very useful way. They respond to heat by rearranging themselves into different, more thermally stable forms, the same atoms, reorganized into a more comfortable shape. And once they have rearranged, they stay rearranged. The oil and gas industry has used this for decades to work out how hot a source rock got, and therefore whether it ever cooked its organic content into petroleum. It is a mature, calibrated, unglamorous branch of chemistry, which means a frictional heat pulse that lasted 4 seconds, 30 million years ago, left a permanent chemical fingerprint on the rock it passed through. It is a thermometer that was switched on for the duration of an earthquake and then locked in that position forever. Pratigya Polisar and Heather Savage worked out how to read it. They developed the technique and refined it first on faults in the northeastern United States, then in Alaska, then on rock recovered from offshore Japan, establishing that you could take a slip zone, measure the alteration of the biomarkers in it, work backward to the peak temperature, and from the temperature work backward to how far the fault had moved. And how far a fault moves is directly related to how big the earthquake was. There is a subtlety in that chain worth naming, because it is where the uncertainty lives. Temperature does not depend on slip alone. It depends on how much slip, how fast, spread over how thick a zone, with how much friction resisting it, and how long the heat had to escape before the rock cooled. Every one of those is a variable. What the geochemists do is run kinetic models. The chemistry of the biomarker reactions is known well enough to say how much alteration a given temperature produces over a given number of seconds, and then work out which combinations of slip and friction could have produced the alteration actually observed. It is not a ruler. It is a constraint, and the answer comes out as a range. The other end of the chain is more solid. The size of an earthquake is set by 3 things multiplied together: how stiff the rock is, how much fault area moved, and how far it moved. That product is called the seismic moment, and magnitude is just a compressed way of writing it down. 2 of those 3 are reasonably well known for this fault, so if you can pin down the slip, you can pin down the earthquake. So in 2022, a team applied that method to the Safodi cause. The paper is called History of Earthquakes Along the Creeping Section of the San Andreas Fault, California, USA. It was published in the journal Geology, and the authors are Genevieve Coffey, Heather Savage, Pratigya Polisar, Sidney Hemming, Gisela Winkler, Stephen Cox, and Kelly Bradbury. Coffey was the lead author, and she did the work as a graduate student at Columbia University's Lamont Doherty Earth Observatory. They looked at a band of highly disturbed sedimentary rock in the core, lying between 3,192 and 3,196 meters below the surface. 4 meters of rock, blackish, crumbly, chewed up. And you might reasonably ask how 100 separate earthquakes fit into 4 meters of anything. The answer is that faults are lazy. When a fault has a surface that has already failed, it prefers to fail there again rather than break fresh rock. The existing surface is weaker, smoother, already prepared. So slip localizes. Event after event uses the same millimeter-thin planes, stacking heat pulse on top of heat pulse in the same narrow bands. That is why the record is legible at all. 4 meters of rock can hold 100 earthquakes because the earthquakes kept reusing the same handful of scars, and in those 4 meters, they found the signatures of more than 100 earthquakes. Let that number stand on its own for a second, because it is the entire reason this video exists. More than 100 separate heat pulses recorded in 4 meters of rock inside the section of the San Andreas fault that is not supposed to have earthquakes. Then it gets worse, or better, depending on your temperament. Because the method does not just detect that slip happened, it estimates how much. In most of those events, the rock says the fault jumped more than 1.5 meters. 1.5 meters, about 5 feet, in seconds. To put that in proportion, the magnitude 3.94 that started this video moved its patch of fault by something on the order of a centimeter. The rock in the Safford core is recording events that moved the fault by more than 150 times that, over an area thousands of times larger. That is not a magnitude 4, that is not a magnitude 5. Slip of 1.5 meters corresponds to an earthquake of at least magnitude 6.9. And to give that a shape you already know, magnitude 6.9 is Loma Prieta, the 1989 earthquake that collapsed a section of the Bay Bridge and killed 63 people. Magnitude 6.7 is Northridge, more than 100 times, on the harmless section. It is worth knowing who did this work because the spread tells you something about how it was done. Coffey led it out of Lamont Doherty and has since moved on to GNS Science in New Zealand. Savage and Polisar, who built the technique, are now at the University of California, Santa Cruz. Hemming and Winkler, both Lamont geochemists, handled the dating side. Bradbury, at Utah State, is a specialist in the structure and mineralogy of fault rock, the person who can look at a piece of core and tell you which parts of it actually slipped. This is a chemistry technique, a dating technique, and a structural geology problem stitched together by 5 institutions, which is why it took years and why the result carried weight when it landed. And the authors are explicit that this is a floor rather than a ceiling. Many of these events could have been considerably larger, because the method of converting heat to slip to magnitude is still being refined, and the refinements have generally pushed in the direction of larger rather than smaller. Here is Coffey, in her own words. This means we can get larger earthquakes on the central section than we thought, and then, immediately after, we should be aware that there is this potential, that it is not always just continuous creep. I want to point out what that quote does not contain, because the restraint in it is the most professional thing in this entire story. There is no timing in it. There is no probability. There is no forecast, no warning, no advice, no number of years. She is not telling you a large earthquake is coming to Central California. She is telling you the category exists and that it should be on the list. That distinction is going to matter enormously in about 20 minutes when we get to the people who disagree with what this finding means. But before we get there, we have to deal with the obvious problem, because more than 100 earthquakes of magnitude 6.9 or larger recorded in 4 meters of rock is either the most alarming fact in Californian seismology or an interesting note about the Miocene, and which one it is depends entirely on a question the biomarkers cannot answer. When? Part 9. A clock that was reset. Burnt molecules tell you that an earthquake happened. They do not tell you when it happened. That is a serious problem, and the team knew it was a serious problem, so they went after it with a second technique that is genuinely clever. Rocks contain potassium. Potassium decays, very slowly, into argon, a gas which stays trapped in the crystal structure of the mineral it formed in. Because the decay rate is known precisely, the ratio of argon to potassium in a rock is a clock. More argon relative to potassium means more time has passed since the mineral formed. This is one of the oldest and most trusted dating methods in geology. It is how the age of the Earth was pinned down, how the timing of the dinosaur extinction was fixed, and how most of the geological timescale beyond the reach of radiocarbon was built. The method has a concept attached to it called the closure temperature, the temperature below which a mineral holds onto its argon reliably, and above which the argon starts leaking out faster than the decay can replace it. Below closure, the clock runs. Above closure, the clock empties. Now here is the trick. Argon is a gas, and gases escape when you heat them. Heat a rock enough, and the argon that has been accumulating inside it for millions of years diffuses out. And when the argon leaves, the clock resets. The rock now reads as younger than it is, because the argon inventory that was measuring its age has been vented. So consider what happens beside a fault slip zone. In the slip zone itself, the temperature spike is enormous and the biomarkers record it. A few centimeters away, the rock does not get hot enough to alter organic molecules, but it does get hot enough to drive out some argon, which means the rock on either side of every one of those 100 slip surfaces should read artificially young, and the amount by which it reads young is a record of the heating. That is exactly what they found. To appreciate the result, you need to know what these sediments are, because they have had an unusual career. They formed tens of millions of years ago as mud on the floor of an ancient Pacific Ocean basin, a basin that no longer exists. The plate carrying that sea floor was subducted beneath the western edge of North America, dragged down under the continent at an angle, and in the process some of the sediment riding on top of it was scraped off against the overriding plate like snow off a plough. That scraped-off material got jammed into the margin of California, buried, squeezed, and eventually caught up in the fault zone, where it now sits 3 kilometers below a cattle ranch in Monterey County, being sheared a few centimeters a year. Before it was fault gouge, in other words, it was the bottom of an ocean that has since been swallowed. Its true age is far back into the Cenozoic. The potassium-argon clock in the rock surrounding the slip zones reads as young as 3.2 million years. And here is where I have to slow down and be careful, because this is the single most misrepresented number in this entire story, and I would rather bore you with precision than let you carry away something wrong. 3.2 million years is not the age of the earthquakes. It is an upper limit. The reason is that the team cannot currently determine how much argon was driven out. If the heating vented all of it, the reset is complete and the clock is honest. If the heating vented only some of it, the clock is only partially reset, and the age you measure is a mixture of the true age and the reset age, which means the earthquakes are younger, potentially much younger, than the number suggests. Coffey has said so directly. Some of these events, in her assessment, could have taken place as recently as a few hundred or a few thousand years ago. A few hundred years. That is not geology. That is history. That is inside the period when Spanish missions were being built along this coast. Now, there should be an independent way to check this, and there is, and it is the standard tool of the trade, paleoseismology. The method is beautifully simple in principle. You find a spot where the fault crosses ground that has been quietly accumulating sediment for thousands of years, a marsh, an old stream channel, a sag pond. You dig a trench across the fault, far enough down to expose the layering, and you scrape the walls clean and map them centimetre by centimetre. Undisturbed layers lie flat and continuous. A past earthquake shows up as a break in that continuity, a layer sheared and offset, a crack filled with material from above, a wedge of collapsed soil that fell into a fissure the moment the ground tore. Then you take charcoal or plant fragments from the layers above and below each disturbance, and radiocarbon date them, and the earthquake is bracketed in time. Do that at enough sites and you get a list of ruptures going back thousands of years. It is how we know the recurrence intervals of the northern and southern San Andreas, and it is the backbone of every hazard model in the state. Trenches have been dug across the central section. They have found no evidence of surface rupturing earthquakes in the last 2,000 years, which sounds decisive and is not, for two reasons. The first is that 2,000 years is roughly the detection limit for trenching in this terrain. Beyond that, the record simply is not legible. So the trenches are not saying no earthquakes ever. They are saying nothing in the window we can see. The second reason is more fundamental, and Morgan Page of the United States Geological Survey put it more clearly than I can. The creeping section is a difficult place to do paleoseismology because evidence for earthquakes can be easily erased by the creep. Read that sentence twice, because it is the key to the whole video. On a normal fault, an ancient rupture leaves a scar, an offset layer, a fissure filled with younger sediment, a buried soil horizon shoved sideways, and that scar sits there, undisturbed, until somebody digs it up. The fault is quiet between earthquakes, so the evidence is preserved by the quiet. On this fault there is no quiet. The ground keeps moving 30 millimeters a year, every year, forever. Whatever scar a great earthquake leaves gets smeared, dragged, sheared and ground away by the ordinary daily business of a creeping fault. The fault destroys its own history, and a fault that destroys its own history will always, always look safer than it is. Not because anyone is hiding anything, because the filing system is on fire, which is why the scientists who work on this problem do not agree with each other. And the disagreement is not a minor technical quibble, it goes to the middle of the question. Part 10. The disagreement. Two people can look at the same 4 meters of rock and reach opposite conclusions about what it means for the people living on top of it. That is what happened here, and I want to give you both positions properly, in their own words, because the disagreement is more informative than either side would be alone. Start with the position that follows most directly from the finding. Morgan Page is a seismologist at the United States Geological Survey, and she is a co-author of the official California Earthquake Hazard Assessment, the model used to set building codes and to price insurance across the state. She is, in other words, one of the people whose job it is to decide what the state officially believes about earthquakes. On the coffee result, she said, "If this holds up, this is the first evidence of a big seismic rupture in this part of the fault." And then she followed the logic where it goes. If a large earthquake can tear through the creeping section, then it becomes possible for a rupture to begin at the southern tip of the San Andreas, travel north through the central section, and continue all the way to the northern end of the fault. That scenario has a name, and everyone watching this already knows it. It is the one people mean when they say the big one, not a magnitude 7 in one section. The whole thing, end to end. Page's own word for the probability of that was remote, and I'm not going to skate past that word, because it is doing real work. Remote does not mean impossible. It also does not mean overdue. It means the tail of a distribution, and the responsible way to hold it is exactly the way she holds it, as a scenario that should be in the model rather than out of it. Her reaction to the study itself was not alarm, it was interest. I'm excited about this new evidence, and hope we can use it to better constrain this part of our model. Now the other side, and this is the most important voice in the video. William Ellsworth is a geophysicist at Stanford University, and he has led research at the Safady drill site, which is to say, this is not an outsider critiquing a finding from a distance. This is somebody who has worked on the very hole the rock came out of. His response: most earthquake scientists think that they happen rarely, as tectonic strain is not accumulating at significant rates, if at all, along it at the present time. Take that sentence apart because it is not a dismissal. It is a distinction, and it is the correct one. Ellsworth is not saying the burn marks are fake. Nobody is saying that. He is not disputing that more than 100 large ruptures are recorded in the rock. What he is saying is that a fault which is currently paying out 26 to 33 millimeters a year against a demand of 34 is a fault that is currently accumulating almost nothing, and you cannot release what you have not stored. That is not a matter of opinion or interpretation. It is conservation. So the biomarkers describe what this fault has done across geological time, under conditions of friction, fluid pressure and mineralogy that we cannot reconstruct and that we have no reason to assume match today's. The creep rate describes what the fault is doing this decade, measured directly with instruments right now. Those are two different questions, and both answers can be true simultaneously. The creeping section has hosted great earthquakes. The creeping section is not currently loading toward one. There is no contradiction there at all, and anyone presenting this study as evidence that California is about to be destroyed has quietly swapped one question for the other. The third voice belongs to Stephen Cox, a geologist at Lamont Doherty and a co-author on the paper, so someone with every incentive to make his own findings sound as dramatic as possible. What he actually said was, people should not be alarmed. Building codes in California are now quite good. Seismic events are inevitable. Work like this helps us figure out what is the biggest possible event and helps everyone prepare. That is a scientist telling you the correct emotional response to his own paper, and the correct response is not fear. It is a slightly larger number in a planning document. I want to underline how unusual that is, because it runs against every incentive in modern research. Cox is a co-author. His name is on the paper. A more alarming interpretation would mean more coverage, more citations, and more attention for the work. He had the option, and he did not take it, and neither did Coffey, and neither did Page. Every named person in this story went out of their way to install a brake. That is worth remembering the next time you see this study repackaged by somebody who did not write it. Which brings us to the planning document itself, and to the part of this story I find most satisfying. The official California hazard model already contained the possibility of a large rupture tearing through the creeping section. It had been put in there years before this study, on the basis of mathematical modelling. You build a system of connected faults, you let ruptures propagate through it according to physical rules, and some fraction of the simulated ruptures cross the creeping ground. And its inclusion was controversial, precisely because there was no evidence. Critics argued, entirely reasonably, that the model was generating scenarios the real world had never produced, and that putting an unobserved event into a hazard calculation inflates risk on the basis of arithmetic rather than observation. This is not a trivial argument, by the way. Hazard models set building codes and insurance premiums. If you tell the model that a rupture can run the full length of the state, the model produces higher expected shaking across an enormous area, and the cost of that shows up in concrete and in premiums paid by millions of people. You do not add a scenario like that on a hunch. You need a reason. Then a graduate student ran a chemistry technique on 4 meters of drill core and found more than 100 of them. Here is how the authors themselves close the paper. Ultimately, our work points to the potential for higher magnitude earthquakes in central California and highlights the importance of including the central San Andreas fault and other creeping faults in seismic hazard analysis. That is the whole finding stated without drama. Not, a great earthquake is coming. Include it in the analysis. There is one more detail in the paper that changes the shape of the hazard considerably, and it gets almost no attention. The authors note that these ruptures may have originated within the central section, or, in their assessment more likely, may have started to the north or the south and propagated through it. Those are very different situations. If great earthquakes nucleate inside the creeping section, then the creeping section is a hazard in its own right, capable of generating a large earthquake from a standing start, and the safety argument based on the slip deficit is in serious trouble. But if they started elsewhere and merely passed through, then the creeping section is not a source, it is a gate. And the question is not whether it can produce a great earthquake, but whether, when a great earthquake arrives from one direction at 100 kilometers an hour, this ground can be forced to carry it. The 1857 rupture arrived and was stopped. The 1906 rupture arrived and was stopped. Twice the gate held. The rock says it has not always held, and a gate that holds twice out of an unknown number of attempts is a very different object from a wall. 2 successes is a small sample. If you had watched 100 coin flips, you would know something about the coin. We have watched 2, both in the last 2 centuries, on a structure that has been in place for millions of years. What would make the difference between a hold and a failure? Nobody knows for certain, and that uncertainty is the honest end of this thread. It could be how far the rupture had already run when it arrived, and therefore how much momentum it carried. It could be the state of the creeping section at that moment, whether it happened to be in the middle of one of those creep transients, temporarily slipping fast, or sitting quietly at background rate. It could be fluid pressure. It could be the direction of approach. What is not in doubt is that the barrier is not a property built into the rock. It is a behaviour, and behaviours have conditions. So the swarm at Pinnacles is almost certainly nothing, and the fault it is happening on is not the fault anybody thought it was. Both of those sentences are true, and holding them at the same time is the honest position. Which leaves one question worth the rest of this video. If the shaking is not where the danger is, then where is it? Part 11. The Gate. At Parkfield. The creeping section has 2 ends, and both of them are where the real problem lives. We have spent most of tonight in the middle of it, under a national park counting small earthquakes. But the middle is the part that behaves. It is the ends, the 2 places where sliding ground meets stuck ground, that decide whether any of this ever matters to a city. Go to the northern end first. San Juan Bautista is a small town in San Benito County built around a Spanish mission, and it sits on the northwestern limit of the creeping ground. North of it, the San Andreas is locked all the way to Cape Mendocino. South of it, the fault starts sliding. On the morning of April 18th, 1906, A rupture that had begun offshore near San Francisco tore south past Daly City, past the Santa Cruz Mountains, and ran out of fault here. The southern end of the 1906 break is essentially at San Juan Bautista. Beyond it, the ground was already moving, and there was nothing left to break. The mission church there is worth a mention, because it makes the geography physical in a way a map does not. It was built at the end of the 1700s, and it was built directly on the edge of the fault scarp, the low step in the ground where the two sides have been offset. The Spanish did not know what they were building on. They knew there was a convenient terrace with a good view over the valley, and the terrace was there because the San Andreas made it. The church has been damaged by earthquakes repeatedly in the 2 centuries since, including in 1906. So the northern gate of the creeping section has a building on it that predates the United States, and the ground it stands on is the last thing the 1906 rupture touched before it stopped. Now go to the southern end, back to Parkfield, and here I want to correct something I have probably let you assume. Parkfield is not a line. There is no point on the San Andreas where the fault is creeping on one side of a fence post and locked on the other. What a transition zone actually is, physically, is a change in proportion. Imagine the fault surface tiled with patches, some of which are stuck and some of which are slipping. In the middle of the creeping section, almost all of them slip and a handful, like the one under Pinnacles, stay stuck. Move southeast toward Parkfield and the stuck fraction rises. Slipping ground and stuck ground interleave, and the stuck patches get bigger and more numerous. Keep going and eventually the stuck patches merge, connect, and the whole surface is locked. Parkfield sits in the middle of that gradient. It is not the border, it is the blend zone, a place where enough of the fault is stuck to produce a magnitude 6, and enough is slipping to stop it becoming anything larger. That is what the 2004 earthquake demonstrated. A magnitude 6 is what this transition can build and release on its own. The rupture ran a couple of dozen kilometers and stopped, not because it hit a wall, but because it ran out of stuck ground to break, and there is an elegant way this interleaving has been measured, which is worth knowing because it is one of the more ingenious tricks in the field. Scattered through the Parkfield transition are tiny patches, a few meters across, that produce the same small earthquake over and over, identical waveforms magnitude 1 or 2 at intervals of months to years. These are called repeating earthquakes, and each one is a single stuck spot being dragged to failure by the creeping ground around it, which makes each of them a gauge. If you know how much slip a magnitude 1.5 patch produces when it fails, and you know how often it fails, you can divide one by the other and get the creep rate of the surrounding fault, at depth, kilometers below any instrument on the surface. Hundreds of these families have been catalogued along this section. They are in effect a network of naturally occurring creep meters buried inside the fault, installed by the fault itself, and what the transition also does every day is deliver. Here is the sequence, step by step. The plates push. The creeping section responds by sliding 30 millimeters a year. That sliding displaces the rock at the southeastern end of the creeping ground by 30 millimeters. But the rock immediately southeast of that, the locked reach, does not move. So the difference has to be absorbed as strain in the transition and as stress transferred across it onto the locked ground beyond. That transfer is small. It is not an event. Nothing about it is dramatic. But it happens every year without interruption, and it has been happening continuously since the last time the locked ground let go, which was January 9th, 1857. 169 years. 30 millimeters a year times 169 years is a little over 5 meters. 5 meters of motion that the plates have demanded, that the creeping section has delivered, and that the locked ground southeast of Parkfield has not returned. You can go and look at what that eventually produces. The Carrizo Plain is about 100 kilometers southeast of Parkfield, and it is one of the most photographed pieces of geology in the world. A treeless valley where the San Andreas runs as a visible scar across open ground, plain enough to see from an aircraft and in satellite imagery, plain enough to trace with a finger. What makes it famous is the streams. Small drainages run down out of the hills, cross the fault, and continue on the other side. Except they do not continue in a straight line. Each one takes a hard right turn at the fault, runs parallel to it for a stretch, then turns back and carries on. At Wallace Creek, the offset is around 130 meters. Those bends are earthquakes. Each great rupture displaced the channel sideways by several meters. The stream cut a new path. The next rupture displaced it again, and the total is the sum of every earthquake since the channel formed. It is a ledger written in dry creek beds, and the most recent entry in that ledger is the one from 1857, which moved the ground at Wallace Creek by something in the region of 9.5 meters in a matter of seconds. 31 feet. Stand on one side of the fault, have a friend stand on the other, and after the shaking stops, they are no longer in front of you. They are a third of the way down the block. That single displacement is nearly twice the 5 meters of slip deficit the locked reach has accumulated since, which tells you something reassuring and something less so at the same time. The fault is not yet carrying as much as it discharged last time, and it is well over halfway there. And it is legible for exactly the reason the creeping section's record is not. Nothing out there erases it. The Carrizo is locked. Between earthquakes, the ground does not move at all, so a scar cut into it in 1857 is still exactly where it was left. The evidence survives because the fault is doing nothing. Now I have to put a limit on all of this, because there is a version of this video that turns the Pinnacle's swarm into a trigger, and that version would be dishonest. Nothing in that swarm measurably changed the load at Parkfield. The arithmetic is not close. The entire 6 days of activity, all 59 earthquakes added together, released a small fraction of the energy of a single magnitude 5. Meanwhile, the creeping section delivers its 30 millimeters a year continuously, which over any given week is a far larger transfer of stress toward the locked ground than the swarm produced in total. A quiet week at Pinnacles loads Parkfield more than a noisy one, because the loading comes from the creep, not from the earthquakes. So why does the mechanism matter at all, if the swarm does not move it? Because it is the reason to watch this section rather than ignore it. The creeping section is not a bystander in Californian seismic hazard. It is a component with two jobs. It absorbs plate motion in the middle, and it hands stress to locked ground at both ends. Anything that changes how it does either of those things changes the problem at the ends, and the coffee team's more likely scenario is precisely a scenario about the ends. If those 100+ ruptures started to the north or the south, and drove through this ground rather than starting inside it, then what the rock is telling us is not that the creeping section generates great earthquakes. It is that the creeping section can be forced to conduct one, which reframes the whole question. The issue is never whether 150 kilometers of creeping fault can build a magnitude 7.9 from nothing. Everything we know says it cannot. The issue is whether, when a magnitude 7.9 arrives at its boundary travelling at 2 or 3 kilometers a second, this ground stops it, or gets dragged along. And that brings us back to where we started tonight. Every one of those 59 earthquakes under Pinnacles is the creeping section doing exactly the job that is supposed to keep an 1857 rupture from ever reaching San Francisco. Every one of them is stress leaving the system. That is the fault working. And the rock from the far end of that same fault says the job has failed more than 100 times, which means that if the shaking is the fault working, then the frightening data in California right now cannot be the shaking. Part 12. The Quiet Faults. Seismicity measures release, not danger. That sentence is the inversion this whole video has been building toward, and I want to state it as plainly as possible before we look at what it does to a map. When you watch earthquakes appear on a live feed, you are not watching risk accumulate. You are watching it get spent. The dots are receipts, which means the most dangerous ground on any fault system is usually the ground with no dots on it at all. So let us look at what the rest of California was doing during the 6 days that Pinnacles produced 59 earthquakes. The San Francisco Bay Area recorded 11 located earthquakes in a week. 11. And essentially all of them were below magnitude 2.1, micro-earthquakes, the sort of event that never leaves the instruments. There was almost nothing on the northern San Andreas itself. Somebody watching that region day after day would describe it, accurately, as a rinse and repeat of nothing happening. Southern California, on the day of the largest Pinnacles event, produced nothing above magnitude 2.5. The single most interesting event down there was a magnitude 1.5 at the junction, where the Garlock Fault meets the San Andreas, a structurally fascinating spot, and an earthquake with about as much energy as a small quarry blast. Now, apply the inversion. Those two regions are where the deaths are. The northern San Andreas killed 3,000 people in 1906. The southern San Andreas system killed 60 in 1994, with a fraction of its capability. Between them, they represent the overwhelming majority of the earthquake risk in the most populous state in the country. And in that week, They produced 11 micro-earthquakes and a 1.5. They were not releasing, they were loading, and it is worth being specific about what is loading up there, because the Bay Area is not one fault either. Running under the eastern side of San Francisco Bay, under Oakland, Berkeley, Hayward, Fremont, directly beneath freeways, water mains, hospitals and a football stadium, is the Hayward Fault. It last ruptured on October 21, 1868, in an earthquake that was called the Great San Francisco Earthquake for the next 38 years, until 1868 was demoted by 1906. Paleoseismic work on the Hayward puts the average interval between its ruptures at around 150 years. It has been 158. Roughly 2.5 million people live directly on top of it. And during the week we have been discussing, the Hayward Fault produced essentially nothing. It sat there. It is sitting there right now. Take the southern San Andreas specifically. Work published in 2026 put the stress on the southern San Andreas and the neighbouring San Jacinto Fault at a 1,000-year high, meaning the current accumulated load is at or near the highest level in 10 centuries of modelled history, and it is stacked around a structure called Cajun Pass, where the two faults come close enough that a rupture on one might jump to the other. Whether it jumps is the difference between a large earthquake and a very large one. Researchers have taken to calling that kind of junction an earthquake gate, a place where a rupture arrives and the geometry decides whether it stops, continues, or branches onto a second fault. Cajun Pass is the most consequential one in Southern California, because a rupture that stays on the San Andreas is one problem, and a rupture that jumps onto the San Jacinto and drives into the inland valleys is a substantially larger one. Interstate 15 runs through that pass. So does the main rail line, so do the aqueducts that carry water into the Los Angeles basin, and so do the electricity transmission corridors. It is simultaneously a seismic hinge and the throat through which Southern California is supplied, which is a useful thing to hold next to everything else tonight, because it is the same structural question we have been circling for 2 hours, transplanted 400 kilometers south. Does a rupture arriving at a boundary stop, or does the boundary carry it? Then there is the Coachella Reach, at the far southern end of the San Andreas. The last major earthquake there was around 1680. Estimates of its recurrence interval run somewhere in the range of 180 to 230 years. 1680 to today is 346 years, and the Coachella Reach is not a remote piece of desert in hazard terms. It runs up the eastern side of the Coachella Valley past Indio and Palm Springs, and the modelled scenarios for a rupture there generally have it tearing northwest, through the San Gorgonio Pass and into the Los Angeles basin from the direction that funnels the shaking most efficiently into the sedimentary bowl the city is built in. Soft basin sediment amplifies and prolongs shaking the way a drum skin amplifies a tap. The distance from the fault matters far less than what sits between you and it. I am going to leave that subtraction where it is and let you do what you want with it, with one caution attached. Recurrence intervals are averages of irregular processes, not appointments. A fault that averages 200 years between earthquakes can go 100 and can go 500. Being past the average is not the same as being late, because faults do not know what the average is. What it does mean is that the load is large and has been building for a very long time. Back in July, in our video on the Brawley Swarm, we watched the very southern terminus of the San Andreas light up. 17 earthquakes in the first hour, a magnitude 3.6, a restart of a sequence that had been running earlier in the year. And then it went quiet again. At the time, the interesting part looked like the swarm. With everything we have covered tonight, the interesting part is the quiet that followed it. 17 small earthquakes in an hour is a rounding error against 346 years of accumulated motion, and the same logic applies to the reach between Parkfield and the Carrizo Plain that we just spent 20 minutes on. 169 years, 5 meters of unreturned slip, 0 earthquakes. 0 is the number that should worry you. 59 is the number that should not. I think there is a genuine cognitive trap here, and it is not anybody's fault. Earthquake maps are designed to show earthquakes. That is what they are for. Every tool we have built for watching faults, the live feeds, the maps with the coloured dots, the alerts on your phone, the apps, is a tool for detecting release. There is no equivalent tool for watching a fault do nothing, because doing nothing does not generate a data point. So the entire information environment around earthquakes points your attention at the places where the danger is leaving, and away from the places where it is arriving. There is a further wrinkle, which is that even the big earthquakes people remember can mislead about which fault is the problem. Loma Prieta in 1989 is remembered as a San Andreas earthquake and as a serious event. 63 dead, a freeway deck collapsed in Oakland, a span of the Bay Bridge down, the World Series interrupted on live television. It was a magnitude 6.9 on a strand of the San Andreas system in the Santa Cruz Mountains, and it did not release the northern San Andreas, not remotely. The rupture was too small, too far south, and on geometry that did not match the 1906 break. Californians experienced the most disruptive earthquake in a generation, drew the reasonable conclusion that the fault had let off steam, and the fault had done nothing of the sort. That is the trap in its purest form. A real earthquake, enormous public attention, and a locked segment that carried on loading straight through it. The news cycle inverts it the same way, for the same reason. A magnitude 3.94 next to a national park is an event, and events get written about. 169 silent years on the Carrizo Plain is not an event. Nothing happened today, nothing happened yesterday, and nothing will happen tomorrow, right up until the day something happens that reshapes the state. Put the two numbers side by side one more time, because it is the cleanest statement of what this video is about. 59 earthquakes in 6 days on the section of the San Andreas that cannot hurt you. 0 earthquakes in 169 years on a section that can, which raises a question that follows directly, and that most coverage of California seismicity never asks. If the locked faults are not moving, and the plates are still pushing, where is all that motion actually going? Part 13. Where the strain is going. The Pacific Plate does not care what any individual fault is doing. It moves northwest relative to North America at a rate set by processes in the mantle, and that rate does not pause because the Carrizo Plain is stuck. Roughly 50 millimeters a year of relative motion has to be absorbed somewhere along the boundary, every year, without exception. It is a budget, and the budget always balances. The only question is which account pays. In Central California, the San Andreas takes the largest single share, the 34 millimeters a year we have been working with all night. The remainder is spread across the rest of the system. The Hayward Fault under the east side of San Francisco Bay, the Calaveras, the Macama and Bartlett Springs faults running north through the Coast Ranges, and farther east and south, the San Jacinto, the Garlock, and the belt of faults on the western edge of the basin and range. Every one of those is a payment method, and the split is not subtle. Of the roughly 50 millimeters a year the plates demand, the San Andreas itself carries something like 2/3 of it in Central California, and the rest is distributed east of the fault, a broad zone of deformation running up the eastern side of the state, through the Mojave, into the Owens Valley and north through western Nevada. Faults there move slowly, individually, but there are a great many of them, and collectively they carry a meaningful share of the plate boundary. This is why the state has damaging earthquakes hundreds of kilometers from the San Andreas, in places most people would not think of as fault country at all. The boundary, in other words, is not a line on a map. It is a zone perhaps 100 kilometers wide, and every fault inside it is connected to the same bill. Back on August 6th, we covered a sequence up in the northern Coast Ranges on a fault that had not produced a recorded earthquake in the whole instrumental era, and then produced an escalating swarm topping out above magnitude 4. That is what the budget looks like when it gets paid somewhere nobody was watching. The plate motion did not care that the fault had no record. It had a share to deliver and it delivered it. Now, creep changes the accounting in an underappreciated way. A creeping fault pays its share continuously, in cash, every year, which means the faults around it do not have to cover for it. That is one of the quiet reasons Central California between Hollister and Parkfield is a less alarming place than the stretches to the north and south. The main structure is settling its own account, and the neighbours are only carrying their own. A locked fault does the opposite. It defers, and deferral is not forgiveness. The amount owed does not shrink while the fault is quiet. It grows, and it grows at a completely steady rate that has nothing to do with whether anything is shaking. That is the whole difference between the two halves of tonight in one comparison. The creeping section pays weekly. The Carrizo Plain has been running a tab since 1857, and there is a third payment method, which I want to bring in because it is the closest cousin to what may be happening under Pinnacles right now. In the same window as this swarm, the Cascadia subduction zone, a completely different plate boundary, running from northern California up past Vancouver Island, logged 127 tremor epicenters beneath the Washington end of the margin, while the southern part of the margin stayed quiet, Tremor is not an earthquake. It does not have a sharp onset or a clear arrival. It is a faint, sustained rumble, lasting minutes to days, generated by slow slip on the part of the plate interface that sits below the locked zone. The two sides slide past each other by centimeters over a period of weeks, far too gradually to radiate the kind of energy that shakes buildings, and it would be completely invisible without dedicated instruments looking for it. What makes Cascadia's version so useful as a comparison is that it is periodic. Along the northern part of that margin, these slow slip episodes arrive roughly every 14 months, run for a couple of weeks, migrate along the boundary at about 10 kilometers a day, and then stop. They are so regular that the timing of the next one can be estimated in advance, which is not something anyone can say about earthquakes, and is precisely because slow slip is not an earthquake. So there are three ways a plate boundary can pay. It can rupture, which is an earthquake. It can creep, which is what happens under Hollister, or it can slow slip, which is what happens beneath Washington. Only the first of those makes a sound, and that is why the tremor matters to a story about Central California. Slow slip and creep transients are the same family of process, a seismic slip, moving through a fault at speeds of kilometers per day rather than kilometers per second, releasing strain where it passes and adding load to whatever locked ground sits at its edges. If the leading explanation for the Pinnacle swarm is right, then what happened under that national park in the first week of August was a small, shallow member of the same family, and every one of those 59 earthquakes was a side effect rather than the event itself. The actual event under that reading would have been silent. There were two other reminders during the same window that the plate boundary is wider and stranger than the San Andreas alone. A magnitude 3 class earthquake struck beneath the Sacramento Valley near Corning at a depth of roughly 22 miles, far below the crustal faults, in rock that has nothing to do with the San Andreas system and everything to do with the remains of an old subduction zone still buried under Northern California. And in eastern Washington, south of Yakima, a magnitude 3.1 struck in a reach that had been quiet for a long while. The Corning event deserves a sentence more than that, because 22 miles is a genuinely odd place for an earthquake in that part of California. Crustal faults in the coast ranges bottom out at 10 or 12 miles. Below that, the rock is normally too warm and too ductile to break. It flows instead of snapping. An earthquake at 22 miles beneath the Sacramento Valley is happening in material that should not be capable of brittle failure at all, which means it is happening in something colder and stronger than the surrounding crust. What is down there is the remains of an old subduction zone. Before the San Andreas existed, the western edge of North America was a convergent margin, and slabs of oceanic plate were diving underneath it. Fragments of that system are still down there, buried, cold, and occasionally breaking. Northern California produces a steady trickle of these events, and they are a reminder that the ground under the state has a history that the fault maps do not show. Neither event is significant on its own. Together with the tremor, they make the point. The motion is being absorbed across an enormous volume of the continent, at depths and in places that no single fault map shows you, and only a small fraction of that absorption is ever loud enough to be counted, all of which depends on the counting being reliable, and there is a seismograph station on the Northern California coast that says it is not. Part 14. What the catalogue doesn't say. At a station near Petrolea, on the far Northern California coast, the trace went flat. Not flat as in nothing. Flat as in saturated. A clean, sharp, unmistakable earthquake, big enough on that instrument to drive the recording off the top and the bottom of its range. Anyone looking at the trace could tell you an earthquake had happened, roughly when, and roughly how close. It never appeared in the published catalogue, not delayed, not revised, not listed as provisional, simply absent. And that happens constantly, especially in the north of the state, which is worth explaining properly, because it is the observation at the root of one of the more persistent claims about earthquake data. The claim is that agencies deliberately suppress earthquakes, that events are hidden or downgraded or quietly deleted to keep people calm or to protect property values. And the observation underneath the claim is completely real. There are earthquakes visible on public seismograph traces that never enter the public catalogue. People notice. They are not imagining it. The explanation is unglamorous. Earthquake catalogues are produced by automatic detection algorithms with thresholds built into them. An event has to be picked up by a minimum number of stations, with a minimum quality of arrival times, before the software will generate a location at all. Below that, the signal is real, but the software cannot solve it, and there is no location to publish. Then there is the human layer. Analysts review events by priority, and priority means size and consequence. In a network processing thousands of events a month, small earthquakes in unpopulated areas are the last thing anyone gets to, and often nobody gets to them. And then there is instrument density, which is the biggest factor and the one that explains the geography of the complaint. Southern California is blanketed with seismometers, because that is where the population is and where the funding went. Parts of Northern California are covered far more thinly. Put the identical earthquake in both places, and one of them gets located, characterized and published within minutes, and the other one leaves a mark on a single trace and disappears. That looks exactly like selective reporting. It is actually a map of where the instruments are. Seismologists have a name for this, and they are entirely open about it. It is called the magnitude of completeness, the size above which a catalogue can be trusted to contain essentially every earthquake that happened, and below which it starts missing them. Every catalogue has one. It is not a secret, it is a published parameter. It varies by region and by year, and it is the first thing anybody doing statistics on earthquakes has to work out before they can do anything else. The existence of a completeness threshold is an admission, printed in the documentation, that the catalogue is not a census, which is the opposite of a cover-up. It is the field telling you, in advance and in writing, exactly how much of the picture it cannot see. There is a version of this that runs the other way too. Automatic solutions are frequently wrong, sometimes by a lot, and they get corrected as more stations report and analysts review the waveforms. Magnitudes shift by half a unit, epicenters move by kilometers, depths change by more than that. The magnitude 3.94 at the center of tonight is a reviewed number precisely because somebody went back and fixed it. So what does all of this do to the count? It means 59 is a flaw, not a measurement, not a total, a flaw. The real number of earthquakes that occurred beneath pinnacles between the 7th and the 12th of August is higher than 59, and nobody, including the agencies, can tell you by how much. That does not undermine the rate anomaly, because the same threshold applied to the 313 background events used to calculate it. Both numbers are undercounts in the same direction, which is exactly why comparing them is legitimate. But it does mean that a fault which erases its own long-term record is also, at the short end, being sampled by an instrument network that cannot see everything it does. Two blind spots, at opposite ends of the timescale, on the same piece of ground. Over millions of years, the creep grinds away the scars of great ruptures faster than the trenches can find them. Over the last 6 days, the detection threshold quietly drops events below a certain size out of the count entirely. The middle of that range, the decades and centuries, is the only window where our picture of this fault is reasonably sharp, and it happens to be exactly the window in which the fault has behaved itself. I do not think that is a conspiracy. I think it is a warning about what 150 years of good behaviour is worth as evidence. There were a handful of other things happening in the world during this window, and I want to close them out because in every case the connection back to tonight is the same one. At Kilauea, on the island of Hawaii, the summit inflation curve went flat. Normally that curve climbs as magma refills the shallow reservoir, and each climb runs up to an eruption. This one stopped climbing without producing the sharp decline that would mean the magma had gone somewhere else. It just sat there. The forecast eruption window slid later. It is another monitoring system where the absence of a signal is itself the signal, and where the interesting reading is the one that did not arrive. In Colombia, a magnitude 7.4 that struck earlier in the week has produced almost no aftershocks at all. A single magnitude 5 and very little else. An earthquake that size normally generates hundreds. And on the other side of the Pacific, a magnitude 4.5 struck 108 miles below the central Kuril-Kamchatka arc, inside the stretch that the enormous magnitude 8.8 of 2025 did not rupture. Two more places where the number of earthquakes and the amount of danger are pointing in opposite directions. Space weather during this window was doing essentially nothing. One C-class flare, the weakest category that gets a letter. Two newly emerged sunspot regions with almost no magnetic complexity between them. A 1% chance of anything larger. A minor geomagnetic bump was expected from a glancing encounter with plasma thrown off by a filament eruption days earlier, enough to nudge the aurora a little farther south and no more. Solar activity is the forcing most often blamed for earthquakes, and during this swarm it was quiet, and in any case the swarm started days before the plasma arrived, and the weather. An unusually cool air mass was building over California and the Great Basin for mid-August, running several degrees below normal, with some model runs approaching 20 degrees below normal later in the month. Earthquake weather is one of the oldest folk beliefs in seismology, and it is worth killing with numbers rather than dismissing with a wave. Atmospheric pressure changes across a weather system amount to a few kilopascals. The stress change required to fail a fault is on the order of megapascals. That is a factor of about 1,000. The atmosphere is not merely a weak trigger for earthquakes, it is 3 orders of magnitude away from being relevant, and no arrangement of high and low pressure closes that gap. So let me land where we started. The fault that shakes is the fault that is spending. The fault that is silent is the fault that is saving. Every earthquake you can see on a map is a fault handing something back, and every day of quiet on a locked segment is that segment taking something on. 59 earthquakes appeared under a national park in central California this week, on the one stretch of the San Andreas that scientists have spent a century describing as harmless, and the description is almost certainly correct for this decade and this century, and probably for a great many more. But the only time anybody has ever gone down and looked inside that harmless fault, they came back with 4 meters of rock carrying the burn marks of more than 100 earthquakes, large enough to flatten a city. The creeping section was never a promise. It was a description of the last 150 years, and there is one thing left that nobody can answer yet. 600 meters from where the ground broke on August 11th, a magnitude 4.64 broke in 2011 on the same patch, in the same shallow rock. The sequence was still producing earthquakes on the day this was put together, slower, smaller, but not finished. So the only question that matters this week is whether that magnitude 3.94 was the peak, or the part that came first.